Welcome to Equilibrium Lecture E, where I'd like to talk to you about the very last K value, which is KSP, for our saturated solution equilibrium. Of course, when I have a salt and it dissolves in water, we know very well that the ions dissociate. And so those released ions can then recollide and reform the solid. And of course, if I have that saturated solution, I can get my rate of dissolving to equal my rate of my recrystallizing. And so what is the whole deal here with a K expression? If I do the product of the concentration of the products raised to the power of their coefficients over the product of the concentration of the reactants raised to the power of their coefficients, and solids and pure liquids drop out, what you will notice is the following. You will notice that our salt that we're trying to dissolve on the reactant side is always going to be a solid. So you'll notice that there's never a denominator in this solubility product constant expression. And so yes, we leave out the calcium fluoride in this example because it's a solid. So what you'll notice is it ends up being the cation raised to the power of its subscript times the anion raised to the power of its subscript. And so what we know is also, because it's saturated, it means it has the maximum amount of solid is dissolved. So adding any more solid is just going to sink to the bottom. So just like a Ka was an attempt to tell you how strong a weak acid is, what is the black and white when it comes to solubility? It is soluble and insoluble. And so what do we know? There is no such thing as insoluble. So a KSP attempts to put a number on how soluble an insoluble substance is. If I put a spoonful of calcium fluoride in a glass of water, a couple of grains of it are going to dissolve, and KSP puts a number on that value. But check out the range of values that you will find. You'll see here that our numbers could be as large as to the -3rd or -4th power. Take a look here. You can have like the -3rd. -3rd is a pretty large value as far as it goes. When I compare it to something like this guy is to the -54th. So there is a gigantic range in different KSP values. So without further ado, let's practice. I have copper 1 bromide. That is an insoluble substance. And as a solid, I will tell you that it has a solubility of 2 × 10⁻⁴ molar. So let's write that out. I've got copper bromide. It's a solid. And when I dissolve it in water and I have a saturated solution, I get copper ions and I get bromide ions. So there's our appropriate equation for the dissociation of this ionic compound. It's very similar to the equations you'll find at the bottom of table I with the water over the arrow. And so I see that it's telling me my solubility. So my copper 1 bromide has a solubility, I'll call it S, is equal to 2 × 10⁻⁴ moles per liter, or molar. And so I need to find the KSP value. Okay, let me set up my K expression. I have the product of the concentrations of the products raised to the power of their coefficients over the product of the concentration of the reactants. Oh wait, it's a solid, so it's going to drop out, and set it equal to K, and this is a KSP. So I'm looking for the KSP. There's my X. So what do I know? I either have X's on the left or X's on the right. So if this is in a 1:1:1 mole ratio, and its solubility is equal to 2 × 10⁻⁴, that means this is also 2 × 10⁻⁴, and this is 2.0 × 10⁻⁴. And I can go ahead and plug those guys right in there. 2.0 × 10⁻⁴ squared, and my KSP value is going to equal 4.0 times 10 to the negative 8th. And as per usual, there is no unit for a K value. So now let's try another example, and I'll show you how this one is a little bit different. If I have silver sulfide, that is also an insoluble solid, and we're trying to see how soluble this insoluble solid is. And now what's the difference? I get 2 moles of silver ions for every 1 mole of silver sulfide due to that subscript of 2. And my sulfide ion is -2. So, setting up my KSP expression, product of the concentration of the products raised to the power of their coefficients. And as we said, the solid drops out. So we have no denominator. So that said, look at the difference here. Last time we didn't have any exponents. This time we do. And we have that exponent simply because I have 2 moles of silver ions in silver sulfide, and that gave rise to a coefficient in my equation for dissociation that we learned how to do back in the day. So I want KSP is my X, so that means I have to have numbers on the right. My solubility for this substance is 3.4 times 10 to the negative 17th molar. But now my mole ratio is 1 to 2 to 1. So I can tell you that if Ag2S is 3.4, then that means my sulfide here is also 3.4 times 10 to the negative 17th. But my silver is double. Because of that coefficient of 2, it is 6.8 times 10 to the negative 17th molar. Now I go to set it up. Check out, the guy I just doubled also gets squared because of the KSP expression. So this is 6.8 times 10 to the negative 17th, that's squared, times 3.4 times 10 to the negative 17th. And push those buttons there, and look at how this stacks up quick. Our last guy with just 2 ions was 4 times 10 to the negative 8th. This guy now has a KSP value of 1.6 times 10 to the negative 49. Just like a Ka tells you how strong a weak acid is, the bigger the number, the stronger the acid. Well, this K value tells you how soluble an insoluble substance is. The bigger the KSP, the more soluble that substance is. Check out silver sulfide, 1.6 times 10 to the negative 49, not very soluble at all. So continuing on in the same vein, this will be very parallel. Go ahead and we're going to pause this video and see if you can follow this example that's very parallel to the one we just did. Okay, here we go. We have our copper 2 iodate, and it is an insoluble substance, and it's going to produce copper 2 ions and 2 moles of iodate ions. And so setting up my KSP expression, I get my solid is going to drop out, as we know. And I get my product of my concentration of my products raised to the power of their coefficients and reactants dropped out. So we now have a KSP value given to us. Oh, how interesting. And so what does that mean? Let's see if you made the transition here. What do I know now? If I have the number on the left, I can have X's on the right. So if my solubility is what I'm looking for, I'm going to call it S. And now this is in a 1 to 1 to 2 mole ratio. So if my solubility of my solid is S, this is also S, and this is now 2S. And just like before, check out the guy that I just doubled, I'm also going to square. So this is equal to S, and this is equal to 2S quantity squared. So as I carry that through, I get 1.4 times 10 to the negative 7th is equal to 4S cubed. I'm going to tell you that any 3-ion system is going to follow this exact same format. Whatever gets doubled gets squared, and then your singular one will just be the S. So you'll always end up with that 4S cubed. If I go ahead and solve that for S, the reason why I call it S and not X is just to remind you, that's your solubility. When you solve for S, you're done. So I push my buttons there, and I take the cube root of 1.4 times 10 to the negative 7th divided by 4. I get my solubility directly at about 3.3 times 10 to the negative 3rd, and this is now molarity because it's solubility. So now we know how to talk about KSPs. What's going to happen if I have a saturated solution like this? It's at equilibrium, but now I throw in an ion that it has in common. What's going to happen? If I say, for example, I have this equilibrium system and I decide I'm going to throw in a little bit of copper 2 nitrate. What I know is it has an ion in common, which is copper 2. And I increase the copper 2 concentration. What's going to happen to the equilibrium? Le Chatelier's principle would tell us if I add to the right, I'm going to shift to the left. And you might notice I will move away from aqueous and move towards solid. So that would end up decreasing my solubility. So I need to know about that. My solubility of my solid is lowered if I add an ion that the solution already contains. And as we said, the reason being is that it already contains that common ion. If I have KCl and I decide to add AgCl, that's going to shift the equilibrium to the left, away from aqueous and towards solid, decreasing the solubility. So let's see about how that math might play out. Let's look at calcium fluoride. I have calcium fluoride as a solid, and it's going to produce, of course, aqueous calcium ions and 2 moles of fluoride ions. Setting up my KSP expression, I have my product of my concentration of my products raised to the power of my coefficients, and my reactant drops out because it's a solid. So I want to find the solubility of the calcium fluoride. So we recall that is my S. My KSP was given to me at 4.0 times 10 to the negative 11th. So I have a value on the left. That means my values on the right can have X's, and it's not a problem. So I see that if my calcium fluoride is equal to S, I can see that initially I don't have any calcium ions, but I have initially 0.025 molar fluoride ions from that sodium fluoride. You'll notice that that 1-to-1 mole ratio means that their concentrations are the same. So this guy is, as a product, going to go up by X, and this guy is going to go up by 2X because of that 1-to-2 mole ratio. And so carrying this guy down, my calcium ion at equilibrium is equal to X. And what are we going to do for this 2F, for this guy here? 0.025 plus 2X, guess what we're going to do? The approximation rule. Look at our exponent. It is negative 11. So therefore, I can say this is close enough to 0.025 and call it a day. But I do have to carry the squared down with me. Push my buttons there. And even though I call it S, I should have called it X. I should have called it S. Sorry about that. I'll switch that up right now just so we don't get confused. So S is my solubility, and I'll be done at 6.4 times 10 to the negative 8th molar. So again, like I said, this was actually, I should not have called this X. I should have called it S. So I'll go through and make those quick corrections right there. This is S down by S to S. There we go. There we go. So our last example for today, we're going to do something again very similar. So let's see if you can pause the video and see if you can go ahead and give this guy a try. We take our PbCl2 as a solid, and we're going to dissociate it into lead 2 ions and 2 moles of chloride ions. As usual, we want to find our solubility. So this guy is S. And as we said before, initially we don't have any lead ions, so that guy is 0, but initially we do have chloride from our strong acid there. We know what makes a strong acid strong. It ionizes 100%, so it also produces 100% chloride ions. We know this is going up, and of course, due to that 1 to 2 mole ratio, let's see what we've got going on. Our KSP is equal to the product of the concentration of the products raised to the power of their coefficients, and of course our solid we said dropped out. We had our KSP at 1.6 times 10 to the negative 5th, so that means I'm allowed to have X's, or should I say S's, on the right. This is going to go from 0 as a product, it's going to go up by S, and because of the 1 to 2 mole ratio, this is going to go up by 2S. Carrying this down, my lead ion concentration will be that S, and here we're going to do that approximation rule and call that close enough to 0.20. But I got to carry down my squared. So when I go ahead and push my buttons there for S, I will get the solubility of my lead 2 chloride at 4.0 times 10 to the negative 4th molar. That's all I have for you for Equilibrium Lecture E. I hope you enjoyed it. Have a good day.